Hello, my project is image classification using deep learning, and specifically I have built a dog cat image classifier using the architecture of convolutional neural networks. My motivation to do this can be listed as the following. I wanted to understand and explore the basics of deep learning, why deep learning is better or how it fares in comparison to machine learning. Something that is so simple for humans to do, why is it very hard to achieve in a machine? And image classification being a very new and relatively nascent stage of study, there's a lot of potential applications for it, like using in search engines and how multimedia content is delivered. And also wanted to build a system that achieves a high performance in predicting unlabeled or unsupervised data. And personal motivation is to participate in a Kaggle contest. So first let us see what is the difference between deep learning and machine learning. The main difference between deep learning and machine learning is the feature engineering. In machine learning, feature engineering is tedious, time consuming, and requires a lot of domain knowledge, and we need to do this by ourselves, as in handcraft the features of the images that we are trying to learn or train the systems on. But in deep learning, feature engineering is done automatically by the algorithm itself, by the layers and the complexity of the algorithm. The feature engineering is far faster and simpler to achieve. The system that I have designed for the dog cat image classifier can be briefly explained as 3 steps. The first one is pre-processing the data. The data is from Kaggle. It is a data set of 25,000 images of dogs and cats and about 12,000 test images of dogs and cats. Step 2 is training the model on the training data, and step 3 is evaluating the performance of our model with the given test images. So prior to training the system, the first step is to pre-process the data. As the first elementary step that is to be done is to download this data from Kaggle, the dog versus cat competition, and then we split our training data itself into subcategories of training, test, and validation. Then we do a common pre-processing step of building a zero mean, and we tweak or tune the data according to our requirements, and this involves histogram equalization, which is changing the contrast of the hues of the images, and resizing the images into a uniform 227 by 227 format. In the next slide, I will show you a common example of how data pre-processing is done in my data set. As you can see, the original image is of 3 colors, and through histogram equalization we have adjusted the contrast, so it simplifies the hues and the color ranges, and finally by resizing the image to 227 by 227. The next slide I will discuss about the architecture choice for this project. There are many deep learning techniques that could have been used to achieve the results in this project, such as support vector machines or random forests or even logistic regression, but I have chosen convolutional neural networks for the following. Now a computer would not be able to, a machine or a computer would not be able to distinguish a cat from a dog just by looking at the photo alone. It would need to be able to understand differences in various features such as ears, whiskers, tails, tongues, the texture of fur, and usually in images these features do not exist as individual pixels but rather as groupings or clustering of pixels. In a convolutional neural network, there are 2 main layers, the convolution layer and the max pooling layer. The main innovation lies in the convolutional layer. Now a convolutional layer applies a set of sliding windows across an image. These can be called as filters, and they can be used to tell distinct and shapes and patterns on the image. So a simple example of a convolution would be a 3 by 3 sliding window pixel, and the three possible filters for that are shown in this image. So if you looking for a horizontal line, the filler on the left will activate. If you're looking for a vertical line, the one in the middle will activate. If you're probably looking for a combination of the both, the third image will activate. And convolutional neural networks have many layers. For more complex images, there will be many more layers to extract feature upon feature at each layer. The lower layers may be used to tell edge and lines, while the higher layers can be used to understand shapes. The intuition is, more the layers in your convolutional neural network, the higher accuracy your model will be able to achieve. And there are other kinds of neural networks that are being used. Convolutional neural network is a kind of artificial neural network. There is the feed forward neural network, which is a simple form of the artificial neural network, in which there are three types of layers: the input, hidden, and the output layer. And in each of these neural network layers, there is an activation function, which I have not explained about in my slide, but it is present in my report. The activation functions change the inputs, transform the weighted sum of the inputs that go into the artificial neurons. And for my project, I have used the RELU activation function, which is the most popular one in deep neural networks. In this project, I have used a deep learning framework known as CAFE, which is used for training the convolutional neural network. There are the following reasons for choosing CAFE. One, it is developed by the Berkeley Vision and Learning Center. It comes with a few CNN models such as AlexNet and GoogleNet, and it has a very high speed and performance, and it comes with a repository that is used by researchers and machine learning scientists to share their trained models. This library is called Model Zoo. I will use this later in our project to illustrate how a pre-trained model can be superior to that of a model trained from scratch. Coming to the training phase, the 25,000 images of trained data that exists are labeled priorly as cats and dogs. This is derived from Microsoft's Asira, where human users have gone and identified images of various dogs and cats. So these images are pre-labeled in the training phase, and we split 5/6 of the training data for training and the remaining 1/6 for validation. We could say that these are two subcategories within the training itself to see the correctness of our training, and these are stored in two LMDB databases called train LMDB and validation LMDB. For the training, there are certain configurations that need to be defined, and these are the important files that take care of those configurations. The train_val.prototext defines the network architecture, the parameters to initialize, and the learning rates. Then we can define a solver which takes care of optimization in our project and serves as the file that actually trains a deep neural network. And in deploy, we use this for our testing and validation, and it is almost the same file as the train_val, and it contains weights as well. Once the training is